look at graphs, if this is f of x, this is just the original graph, and I go like this, this here is a local max, and this here is a local min. They're not absolute. Why? Why are they not absolute mins and maxes? Which means the absolute highest and lowest we could go. Because this arrow keeps going past it, correct? It's going to keep going lower, and this arrow is going to keep going higher. So those would be local mins and maxes. We agree? Now, sometimes we can have absolute maxes and mins on our graphs without them being restricted. So for example, if I have an even degree function, polynomial, like this would be my what? What kind of max? Absolute max. Why can this one be an absolute and the other one couldn't? There's nothing going higher. There's no arrows up, correct? What is this? Absolute min? No, the graph keeps going below. What's this? Absolute max? No. This is a local min and a local max. Now, where would those values appear when we were doing what we were just doing? Where were those critical numbers? Where would those values occur? Critical numbers of the what? The first derivative. They'd be the critical numbers of the first derivative, yes? Okay. The critical numbers of the first derivative would be where the max and mins occur. We've talked about this. Okay, what happens if I restrict my domain, though? What happens if I have something like this? So it's a cubic function, but I cut it off. I said it's no longer allowed to keep going. I restrict your x values. Okay? And I'm going to restrict them between whatever this is A and whatever this is B. We agree? Back here, they were local maxes and mins because the graph kept going. Yes? What are these ones now? This is an absolute max because the graph doesn't go any higher because I cut it off. And this is an absolute min. Now your endpoints will end up being critical numbers too. Your endpoints, bless you. But your endpoints can either be absolute maxes and mins or nothing. Nope, because they're not a local max or min. Local max or min has to have a curve, right? They can either be the absolute highest you can go or the absolute lowest you can go or nothing. What are these endpoints? They're just endpoints, correct? Okay, what if I do this instead? What if I do this? Let's first off talk about the endpoints. What is this endpoint? And it can be an absolute minimum because it's the absolute minimum my graph goes. But as for an actual minimum where it curves, like a local maximum, it doesn't do that, right? So your endpoints can be the absolute highest or lowest you go, or nothing, just endpoints. Bless you. This one is an absolute max. Now sometimes one of the endpoints is an absolute min or max, and the other one is just an endpoint. Now what are these? Because they can't go in, they're not the absolute highest and lowest. This would be a local max and a local min. So the local min and local max would actually appear as critical numbers of my first derivative. Yes? Okay, what happens if this is my graph? Don't do it in pen because I'm going to erase some stuff. Okay, we're not going to talk about max and mins for now. We're just going to talk about critical numbers of the first derivative. So this would show up as a critical number of the first derivative, so would this, and so would this. We agree? Those would all appear as critical numbers. What happens though, bless you, if I give you the equation and I say, okay, but I'm restricting the domain like this. Watch. Do I still state that third critical number? Is it critical to this graph anymore? No. So you can get critical numbers, but then when you go to do your number line, you're going to put endpoints on your restricted domain, correct? If your critical number is outside of that, you still can write it as a critical number, but you're crossing and say it's outside the domain, the restricted domain, so we don't use it. Okay? So sometimes we can get critical numbers, but we don't use them because they're actually outside of the number line. When we restrict our number line or our number line with our domain, it goes outside. So now, this would be the absolute max. And this would be the absolute minimum. And what would my endpoints be? Endpoints. That's all they would be. Because endpoints can either be your absolute max or min, or endpoints. They can't be locals. And both those endpoints are not the absolute highest or lowest this graph goes to, so they're just endpoints. Make sense? All right. So that's if I gave you graphs. Well, let's still go over some examples. So, determine the absolute max and min of the following. F of x equals 5 plus 54x minus 2x cubed, which is what I normally gave you, but now I'm going to give you 0, 4 square bracket. So what does that mean? That's my restricted domain. So it's a cubic function which would normally have local mins and local maxes because that's all a cubic function could have, or a point of inflection, correct? But now that we restricted the domain, those max and mins could be absolutes or they could be locals. So let's discuss it. So the first step we want to do is we want to get the critical numbers of it. How do we get the critical numbers of the max and mins? Derivatize the first derivative and set it equal to 0. Derivatize. It's spreading. The word is spreading. It's now going to be derivatized by the end, which is just made up words. Okay, so 5 goes away. 54x becomes 54 minus 6x squared. We set it to equal to 0 so that we can find horizontal tangents because that's when the tangent slope is equal to 0. And solve. So we get 6x squared equals 54. Divide by 6. And normally if you move your x squared equal to 0, but if you're missing the x, you could just solve it. So what's 54 divided by 6? 9. And when I do this with my hand, this motion, what do I have to have? Plus or minus. So x equals plus or minus 3. So those are my critical numbers, we agree. I go to make my number line. My number line is from 0 to 4. What's our problem? Pardon? Negative 3 isn't in there. So, x equals negative 3. It's outside the domain. Now, some people want to say it's extraneous. Extraneous is a solution. It's not an extraneous solution. It's just outside the domain, so we can't use it, essentially. And then we have 0 to 4. Well, here's our 3. We agree? Now, we want to see if that 3 is a min or a max. That's true. We want to do that. What's the fastest way to actually do it? Second derivative test. So unless I ask you for increasing and decreasing, you can just do the second derivative test. So especially when it's a polynomial, that's way faster. So f double prime of x equals negative 12x. And we want to test out 3. F double prime of 3 equals negative 12 times 3, which is negative 36. So then what does that mean this is? This is a maximum. And we know that because when we plug our first derivative critical number into our second derivative, if our answer is negative, it's actually a maximum. If our answer is positive, it's actually a minimum. It's the fastest way to find it. It's called the second derivative test. So we know that we have a maximum, some type of maximum. We have to put local or absolute. We'll figure that out in a second. At 3 and something. If it was just a sheer cubic function without a restricted domain, it would be local because you can't have absolutes under a cubic function, right? All right. How do we find out if it's a maximum or minimum? If I give you restricted domains, you have to find the y values of those endpoints, because if the endpoints are above or below, then it's not the absolute highest or lowest you can go, right? So I need to find out f of 3. This is true. But I also need to find f of 0 and f of 4. Which means I need to plug them back into the original, because I need to know what the coordinates are on the original graph. So I'm plugging them all back into the original. So I get 5 plus 54 times 3 minus 2 times 3 cubed. I think that's just 5. Nope, that's not just 5. Because this is going to be 54. That's 54 cubed. So it's an extra 54, 59. Maybe? I got an aggressively large number. 113? Oh, that's 113? 113? Oh my gosh, no wonder. This is going to be minus 54. This is 354. So it's 108 plus 5. 113. That makes sense. All right. Then we have to find this one. F plus 54. F. Oh my gosh. 5 plus 54 times 0 minus 2 times 0 cubed. I love zeros because they're easy to do. So it's 5. So I know this one has an endpoint at 0 and 5. This one has a value at 3 and 13. 113, sorry. And then this one at 4, we have 5 plus 54 times 4 minus 2 times 4 cubed, 128. $93? Yes. Okay. If it's hard to visualize, we have 3 coordinates. Can we not do like a little tiny sketch for ourselves? Right? So we could technically go a really kind of terrible sketch. Remember, we're not sketching accurately. This is just for us to visualize something. So the end of the world, like it's not the end of the world if it's a little off. So here would be 5. Let's say here would be 93. Here would be 113. Am I allowed to draw graphs like that in real life for marks? No, that's terrible. Well, you could. You just get no marks. And then we have 0, 3, 4. This is really a bad graph because I only have 1 and 2 in here. Right? I'm just doing a quick sketch for myself. Okay? So 1 and 5, 3 and 113, 4 and 93. Connected. Is it a lot easier to visualize what's an absolute max, absolute min, and just an endpoint when you do a little quick sketch? Yes. So, I know 0 and 5 is my absolute min. And I know 3 and 113 is my absolute max. And what is 4 and 93? Just an endpoint. Can't be a local, right? Endpoints can't be local, they can be absolute. Does that make sense? All right. I'm going to have you guys practice it with only polynomials for right now. So I'm going to have you guys do page 281. And I'll post this page into Google Classroom as well with the answers so you can look at it. 47 to 51 odd. So three questions. If you finish this, which you should, because you have time to finish those 3 questions, because we're not doing the big long thing today, make sure you're done that other question with the square root, the x square root 9 minus x. Make sure you're done it because we're going through at the very beginning of class.